I hope that you can hear me. So hello everyone. So thank you for the introduction and for the organization of this conference. So as you know, this session is about theory of deep learning. So I believe that all of you are aware of the great impact that deep learning had on us or had in the recent few years. So in this talk, I will try to give an aspect related to the theory of deep learning. So in the first hour of this session, we had a great talk by Michael Elad, which happens to be my PhD supervisor. And he gave lots of motivation of why we need to give theory for deep learning. I will give a bit another perspective of the motivation, but probably you don't really need it because of the great motivation we had before, but I already prepared the slides, so you will see it again. So at the beginning, I will mention briefly the impact that deep learning had on the computer vision, machine learning society, and other things, and some works that we had in our lab to show that we know to do also some practical stuff beside the theoretical parts that I will mention later. Then I will survey a bit or some of the theoretical works that was done for deep learning, not by my group. And then at the end, I will mention 4 aspects of how getting some understanding of the structure of the data can help us to understand better how deep learning is working. So my take-home message in this talk is that many of the recent works that try to understand why deep neural networks are working or getting the great performance that they're getting focused mainly on the architecture of the neural networks, but didn't take into account the structure of the data. And I will try to convince you that in order to understand better and design better neural networks, you should take into account also the structure of the data that you are processing and not the networks only. And I will give a small practical example at the end. So I will say a few sentences about the impact. So all of you, or most of you, know about the ImageNet dataset where you have over 1 million images. And the goal in this dataset is to classify all the images that you have in this dataset. You have 1,000 categories. And till 2012, the error that was achieved with this dataset was only 26%. In 2012, a great improvement happened in the computer vision field when Alex Kruszewski from the group of Jeff Hinton succeeded to employ neural networks to get improvement of more than 10% in this dataset. And this led to great revolution in computer vision, in image processing, in many other fields, when researchers and engineers finally understood how it is possible to train neural networks in a good way that will give us good performance. Till 2012, most of the community was using handcrafted features and other techniques, and people were thinking that neural networks are a nice tool, but which is not really useful. But then in 2012, the researchers showed how it is possible to use deep learning in a good way that outperform other methods, and this led to a great revolution. And today, if in 2012 we got an error of 15%, today the error rate for the ImageNet is 3.5%, which is better than what we can do as human beings. If you heard about Karpati, which today leads the research labs of Tesla, so he tried to train himself on the ImageNet dataset. He sat for hours, learned all the dataset, and tried to see what the error rate that he's getting, and he got 5% error. So, and today a machine can get 3.5%. So He finished his PhD in Stanford. He's leading the AI group in Tesla. So the fact that machines get better performance than what he got mean either of the two things. Either we shouldn't trust the Tesla cars, or that deep learning is doing really good job. And the impact of deep learning is not unique just to computer vision. We have this plot from 2 or 3 years ago, prepared by Microsoft Research, that show the improvement in speech recognition. And they show that till 2000, there was a great improvement in the task of speech recognition. But then from 2000 till 2010, there was a plateau in this field. And then deep learning entered into the scene, and another great improvement happened. So deep learning impacted lots of fields. And I can mention a lot of improvement that happened in many domains. So it affects disease diagnosis, language translation, video classification, handwriting recognition, sentiment classification, image denoising, depth reconstruction, super resolution, error correcting codes. And deep learning is entering almost any fields. And if you are in a field that you still don't use deep learning, so you should be aware because the storm is coming. And because I will not, and in a random way, I decided to pick some examples of some advances from the recent years in deep learning. And in a random way, I picked just examples that we did. So I will show several works from my group of practical stuff that we did with deep learning. So one example is image denoising. So we trained the neural network to do denoising. Here you can see, this is a joint work with Tarem Ezor-Litani and Alex Bronstein. Here you can see an example of a noisy image. And we, by training a neural network, we got better result than the previous state of the art. And you can compare our result with the previous result. And you can see that we can reconstruct the details of the hair and the eye in a much better way by training a neural network. We also know how to design using neural networks computational cameras. I don't know if you heard about the Litro camera, where you use multiple lenses in order to reconstruct a 3D scene. We have shown in a recent work that using one lens with a mask that is trained by a network, we can get depth accuracy, which is almost equivalent to what you get with the Litro camera, which is much bigger, much more expensive, and has many more lenses. So in the bottom, you can see our result. In the top, you can see the Litro camera result. And in the middle, you can see the result that you get just by training a network on raw data. And here you can see the result of stereo. So using deep learning, we can train also the optics to give us better results that is post-processed by a network that is trained end-to-end. We did the same by training a camera that will give us all-in-focus result. So the student that worked with Shain Malem, he's a fan of the Beatles. So he took the cover of the album of the Lonely Hearts Peppers, because I think it's 50 years for this album, and made it all in focus. I don't know if he can make the Beatles singers all in focus, but at least he can do the cover of the album. In another work, together with Ofir Nabati and David Mendelovich, we worked on Litro camera. We took all the, so as I mentioned before, when you use the Litro camera, you have lots of lenses. Using tricks from compressed sensing, you can compress all the angles into one sensor. And using deep learning, you can reconstruct from this single sensor both all the angles of the Litro camera and the depth from the image. We have also collaborations from people from astrophysics. So you hear a lot of times about exoplanets that are discovered by NASA. So we have a collaboration on finding exoplanets using deep learning. And we also have, we use deep learning to replace the ISP that you have in your phones. So we took the Samsung S7, and trained the network that that can replace the ISP with a network that has the same computational performance, but get better reconstruction results than what the ISP of the camera is getting. With the difference is that we treat the ISP as we treat the camera as a black box because we have no idea what's inside, and just by examples we can get better results. And I think that this is the first work that replaced the whole ISP of a camera by a network. Okay, so as you can see, or maybe you will disagree with me, but I think that we can get great results with deep learning. And the question that is raised is why we can get such great results with deep learning. And usually the answer that you get when you ask this question is that today we have much more data, we have better hardware, and we have better training organization like dropout or batch normalization. Now, this answer doesn't answer the question why deep learning is getting such great results, but it answers the question of why deep learning is getting such great results today. So we are able to get great results with deep learning today that we couldn't get 10 years ago because a network that we can train today in 2 days, we would require 1 year 10 years ago. So no one would try to train a network for 1 year to find that they need to change one of the hyperparameters. So you cannot design networks in this way. Today, when you design a network, you train it for 1 day, see the curve, retrain it again, and retrain it again and again until you get good results. Alexei Efros call it, or at least in the academy, we call it gradient student descent. So, but what's interesting is that we have lots of data and lots of GPUs also for other techniques. And yet, we get great results with deep learning, but not with the competing techniques. So the fact that today we have better hardware and more data answers the question why deep learning is better today, but not why deep learning is better than the others. And this is the question that I will try to answer in this talk. I will just tell you that, if I will be honest with you, we still don't have an answer. Okay, so you can leave the room if you want. But so today you will hear many talks about people that claim that, okay, we now understand why deep learning is working, or so if you hear such a claim, so it's nice, but don't believe the speaker. We still don't have real understanding of why deep neural network is doing. And as Mickey mentioned in the first talk, is that the practice is going much faster than the theory, but at least we try, and hopefully we hope that the steps that we are taking will one day make us understand better how to train deep networks, and then instead of making all the tweaking and requiring an engineer or a student with golden hands in order to train the network and get the best results, maybe better theory will help us to design in a more fundamental way these networks. And this is important in many real-life problems. So for example, in banks in the US, you cannot use deep learning to decide whether to give a loan to a person or not. Through probably a network will give you a better prediction than the current mechanism that is used. And the basic reason is that when a bank needs to decline a request for a loan, the bank needs to send the person what are the reasons for making this decision. When you use deep learning, you just get the decision. You have no idea why the network made the decision. So hopefully, if we'll be able to understand better how the networks are working, maybe we'll be able to cope better with adversarial examples, understand better what we're doing, and use it with more safety in medical, autonomous driving, and other applications. Okay, so just so if you didn't hear before this talk about neural networks, so I will describe in this one slide what neural networks, or what the basic model of neural networks looks like. Of course, there are lots of variants, like skip connections and other things, but all neural networks have this very simple structure. You take an input, multiply it by a linear operation, and then multiply it by a very simple nonlinear operation. This is one layer of a neural network. And then you take this simple structure, concatenate it, repeat it again and again and again a lot. And if you do it, if you concatenate this structure a small number of times, you have neural networks. If you concatenate this structure lots of times, you have deep neural networks. And this very simple, probably stupid structure, which basically you multiply something by a linear operation, and then apply very simple nonlinearity, which I will show in a minute what it is, give you state-of-the-art results compared to many other much wiser techniques where people sometimes spend their whole careers to design them. So if you look at handcrafted features like HOG or SIFT or other strategies that are used, or for example, if you look at techniques that are based on sparse representation that we also use, you find that you have a very nice model, you have very neat algorithms, you understand exactly what happened in each step, and you get nice results. And then you train a neural network that has a very simple structure, you have no idea why it's working, and you get much better results in much faster way. And sometimes, as happened to us in the denoising paper, we got state-of-the-art results, and we were disappointed. Usually, when you get state-of-the-art results, you are very happy, but with the network, we got state-of-the-art results, and then we look at ourselves and say, okay, so we were better than others, but we have nothing smart to say about it. Okay, so we designed the network, we are better than the others, and so what? Okay, so we have other smart things that we did afterwards to improve it, like being class-specific and other things like that, but at least, so if you're in the industry, so you don't care, if you are better than the others, you can sell it. In the academy, if you are better than others, it's also nice, but you want also to understand why. Okay, so in the linear part in the network, if instead of just using a matrix multiplication, you use convolution, you have convolution neural network. In the non-linear part, usually you either use the ReLU, which is basically element-wise maximum between the input and 0, or the sigmoid, or the hyperbolic tangent. All of them are applied element-wise, and usually the most popular choice today, at least with feed-forward neural network, is the ReLU, which is just taking the maximum between the value and 0. And then you have another type of nonlinearity, which is the pooling, which is taking the maximum between several values. And in some networks, you even don't need the pooling. So some work show that if you just use convolution with ReLU, and instead of pooling, you just make convolution with strides, you get the same performance. And again, we have no idea why this works so well when you're doing such simple operations. Now, in some sense, the inspiration for that comes from our brain. We also have these layers in our brain, and we also make very simple decisions at each we have very simple operation at each level of the brain. And at the end, we make the decision. And it's also not very complicated mechanism that lead us to make wise decisions, or maybe they're not so wide and not so wise, but I don't know. Okay, so I will give a sample of some existing theory for deep learning. And when we try to understand why deep neural networks are working, so there are several questions that we are interested to answer. I will pose some of these questions here. Of course, there are many others, but I believe that these are some of the fundamental questions that we are interested to answer. So one important question is, what is so special about the deep neural network structure? If you understand what is so special with the structure, maybe we'll understand that maybe we can change it a bit and get better performance, or understand what is the effect on of the structure on different types of data. Another question is, what is the capability of deep neural networks? Can we use them to solve any problem? Are there problems that we cannot solve with deep neural networks? I think these questions are important, especially when today we use them with autonomous cars, or with medical applications. So when you use deep learning with conventional image processing, for example, for making the photos that you take nicer, it's okay if your photo looks nicer than what you are in reality. Okay? You will like this outcome. But if someone will take a CT of someone which is ill and the network will make his lungs look nicer, I don't think this is a good outcome because it will not heal him. So these questions are really important when we go to real applications. Another important question is how many training samples do we need? So when we use, we want to do classification for cats and dogs, it's very easy to have lots of labeled data using the Amazon Mechanical Turk. But if you want to have labeled data for medical applications, all of us know that paying to a doctor to make the labeling takes lots of money, and also having the doctor seated and making the labeling with all his occupation or her occupation is very hard. So usually when you talk to a doctor, he tells you, okay, I have big data, I have 200 examples. So for him, it's big data. For neural networks, it's not so helpful. So you can use transfer learning, but an important question is when we know that we can tell the doctor, okay, it's enough. Another question is what is the role of the activation function when we want to use sigmoid, when we want to use ReLU. Another question is what happens to the data throughout the layers. What is the role of the depth? Why deeper is better, or whether deeper is always better? Do we have an effect? Can we say that we have an effect of vanishing returns from a certain point where we say, okay, depth of 20 is good, but 40 will give us the same result, and we don't need it, and it's much more computationally expensive. And another question is what is the role of pooling? So there are lots of works done for the theory of deep learning, and some of us, when we think about deep learning, we forget that they existed from the 60s. So deep learning existed in this, or neural networks exist in the 60s, and then a famous book came out, I forgot the name of the author, that said that they're not good, and then the first winter of deep learning came, then deep learning neural networks became very popular in the 90s, and then SVM came into the scene and kicked out neural networks, and now, and the second winter of neural networks came, and now we are in the third spring of neural networks, and some people claim that each time a winter of neural networks came into being was when a new theoretical understanding came into the scene. So when the theory book came in the 60s, the first winter came. When the theory for SVM came, they kicked out neural networks the second time. And maybe if we will be able to understand neural networks again, maybe we'll be able to kick them and bring the third winter. And in Israel, winter is very important. We need rain. So if you remember that neural networks are not something that happened just in 2012, so when we go to theory, we can go back to the 90s, and the very famous theory is the bound by Saibenko and Hornick, which they developed it independently, which is called the universal approximation theory. This theory basically tells us that you can approximate any function that you want. You can approximate any measurable Borel function. For the people in the audience, it's every function you want, using a neural network. Now, when you look at this theory, you may claim, okay, so we have a theory that tells us that we can do anything with neural networks. So we are very happy. We can end my talk here because we can do whatever we want. But the problem with this theory, besides it's being correct, is that though it tells us that we can do whatever we want with neural network, it doesn't tell us how to do that. So let's assume that we have a classification function, and someone tell me, okay, you can approximate the function that solves your problem with the neural network, but I have no idea what is the function. So the fact that someone tell me that I can do it doesn't always help me. The second thing is that this theorem tells me that I can solve any problem with neural network, but it doesn't tell me what is the size of this network. Maybe the size of the network will be close to infinite. Third problem, or not problem, is that this theorem is true for shallow networks, for networks with just 2 layers. And today we know that deeper networks give better performance than shallower networks. And here we know, and this theorem tells us that you can do anything with shallower. So why we need deep? So beyond this theorem that tells us that neural networks are great, we need more things. Another important theorem by Baron from 94 analyzed the approximation error of the networks, and then it showed that the error of the network can be divided to 2 parts. The first part is the part that tells us how well the network can estimate our function, and it depends on the smoothness of the function and the number of neurons. Basically, it tells us that the bigger the network, the better we can approximate any function we want. The second term in this theorem tells us that the more deal with overfitting, and tell us that the more neurons we have, the more training examples we need to solve the problem of overfitting. Other series of works that came after 2012, when deeper networks were used, analyzed the impact of depth of the network on the performance. So this work showed that if you compare a shallow network with a deep network, and you look at the function that the deep network is approximating, so with very high probability, in order to approximate the same function with the shallower network, you will need the exponential number of parameters. So basically, deeper networks are more compact for representing or solving problems. So if you want to solve a problem and you use deep networks, you need much smaller number of parameters. And if you have less parameters, you need less training examples, and you generalize better. And this was shown also by Ted Gasky, by Ohad Cohen, I forgot the first name, by Cohen from in his PhD with Amnon Shashua, and also by Ohad Shamir. Another series of works looked at the role of pooling, and they showed that what pooling gives you with convolution is shift invariant. So if you want to classify a cat, you don't care if the cat is at the right side of the image or the left side of the image, and therefore you want a structure that gives you shift invariance. And this works show that using pooling, you get shift invariance, which is very desirable. Another line of works, which is related to the information bottleneck of Tishby, and then came from the group of Stefano Soato, showed that there is a relationship between the structure of the networks and sufficient statistics. And they showed that network linear sufficient statistics that help you to solve a problem in an optimal way. Another lines of work studied the scattering transform and studied the relationship between wavelets and deep neural networks. And then they showed that neural networks can be used also as a metric to measure distance that is closer to the to the human perception. And they showed that if you usually we know that when you try to solve a regression problem using least squares, you have the problem of regression to the mean. And if you use instead of least squares, instead of L2, you use loss in the scattering transform or in the feature space of neural network, you get sharper edges. So this is a very nice work by Bruna, Sprechman, and LeCun, and then it was extended in the Esser-Gann paper and other works. Other series of works studied the local minima in neural networks. So many people before 2012 experienced a problem, and one of the main hindrances that cause people not to use networks is the problem of local minima. So people would look at the problem, the optimization problem in neural networks, and we say, okay, we are solving a problem which is non-convex, and because it's non-convex, we will get stuck in the local minima, and local minima is not good, and therefore we shouldn't use neural networks. A series of work show us that if you take a deep network and look at all the local minima of this network, so all these local minima are very close to each other, and therefore you don't care if you fall in one of the local minimas because either of the local minimas looks the same. And these works are very interesting because there is a phenomena that many practitioners experience. If you will take the same data and the same network and will train it twice with different initialization, in the two initializations, you will get almost the same performance with the network, but each network will have totally different weights. And this phenomena puzzled many people of how it may happen that you train a network 10 times and you get the same performance, but with different weights. And this line of works started by Zaxe, and then the very nice work by Komreska, showed that the deeper the network, the closer the local minima to each other. And therefore, you don't care if you get stuck in the local minima, but you care if you get stuck in a saddle point, and you have more saddle points in a shallow network than in a deep networks. And there are lots of other works that continued since this work in 2015 that studies how the local minimas look like. So there is a recent work by Daniel Sudri and Elad Ofer and other works. Another work studied also when the local minima is the global optimum in a network. And there is the work by Pian, Romalo, and Elad that show relationship between neural network and the sparse representation, but you had a whole talk about it, so I will skip it. Okay, so till now I surveyed part of the results that were derived for the theory of deep learning, and most of these results consider just the architecture of the network and not the data. And now I will try to show you how, when we consider the structure of the data, we can get better understanding of what neural networks are doing. So at the beginning part, I will try to convince you that deep neural network keep the important information in the data. Then we will see that we can view neural networks as metric learning system. Then we will look at the relationship between the margin that the network achieve and the generalization error. Then I will skip the part that talk about how to solve optimization problem with neural networks because I don't have enough time. And then we will end. Okay? Now, so if you are very tired after lunch, so you can go to sleep, but remember the important point is to understand the performance of neural network, you should take into account also the structure of the data and not the structure of the network itself. So one of the things that you do when you want to analyze a complicated structure is having some assumptions. So we will have some assumptions on the network. Some of them are more realistic, some of them are less realistic, but the more we'll go into the talk, the assumptions will become more and more realistic. But these assumptions give us some notion of understanding of what happens in these networks. So the first assumption is that we will assume that we have networks with random Gaussian weights, and the reason that we assume that we can assume that the networks has random Gaussian weights is that random Gaussian weights is a common initialization in neural networks, and understanding what the network is doing when it is initialized, I believe will give us some intuition of what happens during the training. So now we'll analyze what deep neural networks with random Gaussian weights are doing. So the first theorem that I will present is that if we have a network with small mean Gaussian weights, and mean Gaussian weights basically is a measure for the complexity of the data. If your data is very complicated, let's say ImageNet, it will have very large Gaussian mean weights. If your data set is very simple, let's say MNIST, you will have a very small Gaussian mean weights. And we show that if the network is, has a random Gaussian weights, then, and you have a small mean Gaussian mean weights, the Gaussian mean width in each layer of the network stays almost the same as in the input. The reason that we need this assumption is twofold. The first one is that it's interesting to understand what happened to the complexity of the data throughout the networks, whether the data become more complex or less complex. And we show here that the complexity doesn't increase. The second thing is that once we assume that the complexity remains the same, we can analyze each layer by itself and then get conclusions on the whole network by itself. The second theory, yeah. The relationship to entropy, Gaussian mean widths basically say that you take a random Gaussian vector and take the supermom inner product between a point in the set and take average over all the Gaussians that you take. Okay? So there is a relationship with entropy, but it's more related to the covering number. Another theorem that we showed is that if you look at the relationship between at what each layer of the network is doing to the data, we show that the network is doing tessellation to our space, basically mean that we are dividing the space to small cubes, and then if 2 points lie in the same cube, it means that they were very close to each other at their input. And the reason that this result is interesting, because if we have this property, then we can prove that it is possible to reconstruct the input of a network from the output up to small distortion. And this result stands in line by the work of Mahendra and Vedaldi that shows that you can reconstruct the input of the network from its output, and that the distortion that you get in the reconstruction grows almost linearly if you look at it in an empirical way. Now, till now I showed you what happens with random Gaussian weights. Now we ask the question of what happens if we look at trained data. So we looked at some of the state-of-the-art networks. So we didn't take the ResNet, we looked at the VGG. And we made the following simple example to check what we can say about the change of the metric in the network. So consider the following simple example. Let's assume that we have a point V and the point W, which is a point from another class, which is the closest to V. Okay, so now here I present just two classes for simplicity, but of course we can generalize this to many more classes. So assume that you draw a point V at random, and then you take a point W, which is the closest to this point from another class. Then you measure the distance between them, then you take V bar, the output of this point, and take the point Z bar, which is the closest to V bar at the output of the network, and you measure the distance between them, and we measure the ratios between these two distances. And we call this ratio as the interboundary distance ratio, okay, because we took 2 points from other classes. We repeat the same for the intraboundary distance ratio. We take a point V, and we take the farthest point from it from the same class, and measure the distance. We take the output of the point V, and they take the farthest point from it from the same class at the output of the network, and we measure the ratio between the distances. Now, of course, if the network is doing a good job, you expect that points from the same class will become closer to each other, and points from different classes will become farther from each other. And we see this phenomena. We compare a random network to a trained network, and we see that if we have points from the same class and we draw the histogram of these ratios. So we find that for a random network, most of these ratios are around 1, and for the trained network, most of these ratios are bigger than 1, which means that a trained network make distances farther from each other. And when we look at points from the same class, we see that a random network keep points almost with the same distance to each other, and the trained network make distances closer to each other. Now, I believe that you're not surprised because we expect this thing to happen. And of course, if you look at a random network, almost nothing will happen because it's random. Okay. But of course, we didn't stop here because otherwise it would be trivial. And we repeat the same experiment, but with random points. So we take 3 random points, V, W, and Z, 2 points from the same class, another point from another class, and measure the ratios as before, but now the ratios are between random points and not the boundary points. Before we just took the farthest points and the closest points. Now we just took ratios of random points, and we draw the same histograms. And surprisingly, we get that the histogram of the trained network has very similar behavior to the histogram of the random network. Now here I present the result for the ImageNet. The same happens for CFAR and for other datasets. Now for here we took a pre-trained network. Now if we repeat this example, and we draw the network in different steps of training, you can see that this histogram goes to the right. But when you look at the random thing, you just see that the histogram stays in the same place. Which layer? What? So we took the VGG and we cut the network before the fully connected. Okay, that's the... Yeah, so it's, yeah. So it's not exactly the last layer because you have several fully connected, but we look after the convolutional. So we get that for the boundary points, we get stretching and squeezing of distances, but for random points, you get that the behavior of the trained network is almost like the random network. And this gives us several interesting conclusions. One of them is that our analysis for random networks is also relevant to part of the points in the trained network. Another one is that on average, network preserve distances in the trained and the random networks, and the main difference is with respect to the boundary points. And if you want to train a network with less training examples, you probably need to find these boundary points. And we are still working on it, but I think that this understanding of what the network is doing can give us ways of how to dig better the training examples and how better to train the network and understand what it's doing. Okay? Another result that I will show now is related to the generalization error of neural networks. And in this setting, we assume that we have a very general neural network. Okay, so I will skip this part of the generalization error because I want to talk about the optimization part. I will just say in 2 minutes what is the result that we had. And basically, if you look at the neural networks, let's assume that we have 2 classes. So one way to look at what neural networks are doing is to divide the network to 2 parts. The first part can be viewed as a part that extracts features. The second part can be viewed as a simple classifier. So if we look at the points at the input space, let's assume that we have 2 classes, the blue stars and the red stars. And then let's assume that at the output of the network, we have a linear classifier. So we can think of a network of the things that the network is doing. If we look at the 2D case, that the network is taking these points, they are transferring them to this domain, and then we have a linear classifier, and then we can look at the corresponding line to this linear classifier, to this non-linear line. So basically, when we have a linear classifier at the output, it corresponds to a non-linear classifier at the input. And then we show that the generalization error of the network depends on the distance between the points at this boundary. And we show the relationship between this boundary and the Jacobian of the network. And then we show that because we have this relationship, you can regularize the Jacobian of the network, and in this way get better generalization. And I will skip the theory and the parts related to the generalization error. And I will just mention that by having this understanding that the Jacobian of a network give us better generalization, we can get better results when we train with a small number of training examples. And you can find these results in the paper. And we also showed that if you train an invariant classifier, you get also better generalization. You can train with smaller number of training examples. Okay. So the last thing that I will talk about is about optimization with neural networks. And in this part, I will look at a network with a feedback. So let's assume that we have a network with this structure. We take an input, we multiply it by a matrix A transpose, then we multiply the output with I minus mu AA transpose. We apply a simple nonlinearity, which looks like the ReLU, but is two-sided. We call it the soft thresholding. And it can be shown that this iteration, this iterative process, if we apply it till infinity, it solves this minimization problem, where we have a nonlinear, a linear matrix A multiplying unknown vector Z and the measurement V. And in the talk that Mickey gave, he called this the lasso problem or the basis pursuit. So it can be shown that if you apply this network infinite number of times, which is an iterative algorithm, which is called ISTA, or proximal gradient, you solve this optimization problem. The problem with this minimization problem that is called ISTA is that you need hundreds of iterations to get an accurate solution. And if you want real-time performance, probably you would like to solve the problem with 10 iterations, or 5 iterations, or 20 iterations. And you cannot allow yourself to wait for 1,000 iterations. In a very nice work in 2010, Gregor and LeCun showed that if you take the same structure that I showed before, but you replace the A transpose and I minus mu A transpose, the linear parts, with two other linear parts that you just learned from the data, and then you train these operators using backpropagation to give you the same result that you get from the previous algorithm with thousands of iterations, you can converge to the solution that you want with just 20 iterations. So it's like black magic, but it's as all other things related to deep learning. So basically, you can take an optimization problem, have an iterative algorithm that solves it. You have guarantees for this algorithm, but this algorithm needs several hundred iterations. And then you can train a network that has the same complexity per iteration like this algorithm and converge with smaller number of iterations. And the interesting part here is that this acceleration is not unique just to the lasso, to the problem that I mentioned before. If you look at other optimization problem, if you have an objective which has nonlinearity, like if you look at quantized data, or if you look at simulation flows in physics, you can apply this concept on all these problems and get very good acceleration using neural networks. And thus, in any other thing related to neural networks, we get acceleration, we get greater performance, but we have no idea why. In the next few slides, I will try to give you some notional understanding of why we can do this trick with neural networks and why it's working. So as I mentioned, this acceleration worked for many scenarios, and no theory was available with it. And then we came up with the theory that I present now. In parallel to us, two other works gave other views for the explanation, one by Wipf and the other by Bruna. And I believe that all our explanations complement each other. Okay, so one recent work showed that the complexity of the convergence of this iterative algorithm, if instead of a soft thresholding we have projection onto the L1 ball, depends on the dimension of this vector z. If this vector z lie in a very small dimension, then, and we make a projection onto a small dimension, we will need a very small number of iterations for convergence. If the projection that we are doing here is on a set which is very large, we will need lots of iterations. In our work, we showed that if we allow ourselves to have some errors in this projection, so let's assume that you want to get convergence in 20 iterations, and you don't care if you get an error of 1 to the power of an error of epsilon. So when you do the projection, you can allow yourself to have this small error. And if you allow yourself to do this small error, you can project onto a simpler set, which will give you much faster convergence. Then we said, okay, so if we are doing this thing and we can get this simplification in the projection which give us faster convergence, we can divide the set onto which we are doing the projection onto several small sets and train multiple Lista networks to accelerate the convergence faster. And we get faster convergence than what you get with the Lista. And here you can see that when we get some theoretical understanding as to why a network has a behavior in a certain way, you can design new architectures that will give you faster convergence with the same number or with the same latency. The last thing that I will mention, I will return to the first example that we showed. And when we have understanding of the data, we can solve also real problems in a faster way. So for example, in the denoising case, so we looked at all the literature and we say, okay, so all the denoising problems go to some saturation. But we know that if we know what is the object that we are looking at, whether it is a face or a street or another thing, we will be able to make the denoising in a much better way. And then we came with the idea that instead of regular denoising, we can do class-aware denoising. And of course, when you are taking a selfie with your phone, usually your face appears in it. So if you know a priori that your face appears in the selfie, you can have a denoising algorithm that expects to see a face and make much better denoising and reconstruct the details with a much higher resolution. Also, we know that we have very good classifiers. So why not use a classifier with a denoiser? And we know that classifiers are very robust when you're doing denoisers, and this gives us the opportunity to get much finer reconstructions in the details when we recover images. And it helps us also to make better depth estimation with computational cameras. So just to summarize, in this talk I surveyed several topics related to understanding better deep learning. I showed you that if we have some prior on the data that you are working on, we can do better processing. I showed you that when you work with a neural network, usually neural networks keep most of the information in the data throughout the layers, and this information degrades gradually. Then we showed that when you look at the initialization of the network with random Gaussian weights, the behavior of the network on the average points is almost the same like the initialization. The main change is in the boundaries. And therefore, important goal of the classification is to treat these boundary points. Another part that I didn't talked with details, but I just mentioned, is that the generalization error depends on the deep neural network input margin. And we have seen that one conclusion is that we can view neural networks as symmetric learning. And the last part is that I mentioned that we can solve optimization problems with neural networks. So thank you very much. And I will just mention that the slides that I present, an extended version of the slides that I presented here appear in my website. And if you like this talk, there is a 3-hour tutorial with extended version of this talk that appeared on my website.
Thank you, Raja. Any questions?
It appears that what the neural networks is doing is bumping the boundary from the input domain to the right location in the output domain. So maybe we can learn from your talk that what we were used to do is to try to map, I don't know, the bulk of the input domain to the output domain, to the classification, was wrong, that we only have to look at the boundaries, and if we take the boundaries to the right part, so that should be the strategy, isn't it?
So I think that it is important to focus on the boundaries. But the main challenge is that when you want the boundaries in the feature domain, and they are more interesting than the boundaries in the input domain. And then during the training, you learn where the boundaries are. So this is the main challenge. So sometimes you need all the data to find these boundaries. And the challenge is to understand where is the boundaries with less or in an unsupervised way.
Hi, you mentioned that there were more local minima in a shallower network. I just wanted to understand where the intuition came behind that when you compare deeper networks.
You refer to these slides? Yeah. Okay. So in this line of works, what they're doing, they are looking at networks. In order to make the analysis, they look at the networks without the nonlinear parts, but which are deeper. And then they make a relationship between this structure and a spin glass theory in physics, and show that if you look at the monomials in this theory, you can look at the zeros of these monomials, and then in this spin glass theory, you can show that the higher the order you have, the closer the zeros are to each other. And in a similar way, the deeper the network, the closer the local minima to each other. Now, there are newer works, one of them by Ben Recht, others by the group of Stefano Soato, and there is also a work by Daniel Sudri that also give another perspective into the intuition of when the global minima is related to the local minima, but it take a different perspective. Here you can see that all the local minima are the same. In these works, which are more similar to the one of Havel and Vidal, you ask yourself when you get to the real global minima.
We have time for one last question. Shout out.
You said that we can choose fewer samples if we can choose samples that are related to the boundaries. What is the metric? How do you choose a metric to decide which samples
So if I would know the answer, I would publish a paper about it. We are still looking for it.
How did you choose the metric in the paper?
So here we just trained the network. And we looked at the Euclidean metric at the input and the Euclidean metric at the output. Yeah, we looked at images. And we looked at MNIST, at CIFAR, at ImageNet, and in all of them we saw the same behavior.
Thank you again.